Awesome. So we are live on YouTube and Zoom is working. Change this. Ishtaji is here. क्या बात है? What is that hardware enabled stack? Very weird.
Okay, the hardware enablement stack is more or less the LTS enablement, what Ubuntu says. So it is like they are providing new and updated kernel for LTS support. Since the support is LTS and each LTS is supported, I think, at least 3 years, so things get changed. And for that, they are maintaining backward compatibility and stuff. So they have written that. Now, the thing is, I have connected to my Ubuntu 18, if you can see, and we will be doing everything on Ubuntu 18, 32-bit.
What is the chat, Sanjay?
Yeah.
I'm leaving that meeting for now. Just made you co-host. I'll join by around 5:50 or 8 p.m. Okay, so you guys can continue. I'll join later.
Okay, just a minute. Okay, so starting now. Now, today's agenda is primarily the basics that we are going to be covering for exploit development. So first will be the introduction to Linux exploitation, or more or less the exploit development on Linux, the environment, what we have, what we do not have, what are the requirements when you are starting out. The second thing that we are going to cover is introduction to exploit mitigation techniques. So there are mitigation techniques you guys have heard of, for example, NX or DEP or something like that, right? Then we will be starting with smashing the stack on Linux. Let me just write all this. Unfortunately, I haven't written this. So how many of you have at least attempted to write exploit or attempted to learn buffer overflow exploitation or exploit development on Linux or Windows before? You can record this. I don't think there is any need for that because it is already streaming on YouTube live. So you can anyway have the YouTube video as well. Yeah, okay. So I started learning exploit development. So put these scripts. Okay, so there are a few people who have attempted to learn exploit development. So today what we are going to cover is, since we are covering every single thing on a fully updated Ubuntu system, so there are nothing which is outdated and cannot be applied to today's systems. The first thing is introduction to Linux exploitation. So in this, So when we talk about exploit development, we the current session or the current series is more about exploiting binaries, and uh, and again, in case of exploiting binaries, we are going to exploit memory corruption vulnerabilities such as buffer overflow, format strings, and things like that. So though the idea is more or less limited to stack buffer overflow in the context of current series, but then heap buffer overflows are also there, which are exploited using how do I say this? Yeah, so the heap overflow exploitation is a little bit different than stack based buffer overflow exploitation, just because stack has been more or less same since it has been created in case of process management and stuff, but heap implementations keep changing again and again, as well as new data structures are added to the heap, new protection mechanisms are added. So these things make heap exploitation more or less a platform dependent thing. So though the general idea of buffer overflow exploitation of a stack based vulnerability is more or less the same across Windows and Linux, but in case of a heap based buffer overflow, things are quite different when we come to actual exploitation part. In theory, things are same. You just have to overwrite a few important data structures and you get the code execution. But Linux uses ptmalloc2, or I think ptmalloc3, which is based on dlmalloc. Windows was using its own LFH since Windows Vista. Then now we have moved, in case of Windows 10, there is segment heap. So as heap implementation changes, the exploitation scenarios get changed. And since the series is targeted more or less for beginners, those who want to start with exploit development, we are just keeping it to stack-based buffer overflows. I think that is clear with you, right? Okay, am I audible, or is there some problem with audio?
Yeah, we can hear you.
Okay.
You're audible.
Okay, great. So now moving on to modern mitigation techniques. So as now stack overflows have started getting exploited since I believe 1990s, where when the first paper by LF1 came out by the by the title "Smashing the Stack for Fun and Profit." So since then, Stack Overflow and exploit mitigations have been evolving, coming new and again. So the first thing was like having some. One of the things is having stack cookies. Let's have let's have a look at some GNU binaries, right? So let's see if there is something in bin ls. Let's just load it in. Okay, so this is I'm using Jeff for GDB, which allows you to have a pretty good view, as well as it increases the usability of GDB. It is a simple plugin, more like if you have ever heard of GDB Peda, or the plugin for exploit development and stuff. So it is more like that, but it also provides you cross-platform compatibility as well. So it can also work on, I would say, ARM-based binaries, MIPS-based binaries, as well as it looks a little bit much better, and it supports a wide variety of operations. Now, checksec is initially checksec was a was a like a standalone binary or bash script in of itself, if you have ever heard of it. So what checksec does is it lists various uh, exploit mitigation techniques which are enabled on a binary. So it's starting with the canary. So a canary is something which is placed before a function's return address. Now, usually there are three types of canaries. First one is a totally random value. Second one is a terminator canary, where the canary has terminator values, such as for a string termination, there's a null character. For file termination or end of file character is usually represented by FF. So there's that. Then there's 0A, 0D. So what terminator canary aims towards is more or less, placing all the possible termination characters. So when the function reads there, it just terminates the input or copying on the stack, and the return address does not get overwrite. Right. And the third one is usually a Zord canary, where there is a master canary value, and it is also, and of course it is generated randomly. The thing is, the master canary is Zord with some value when placing on the stack, and then it is checked before returning the function. So the basic idea of canary is, since it is placed before the return address, let's just change a few things. Let's stop sharing. Yeah, great. So there we go. So it is more like here's the buffer and here is the return address, and the buffer is growing this way. So this is the basic usual idea. When we have a canary, the canary comes, let's do this way. The canary is right here. So when a buffer is overflowed, what happens is eventually it will override the canary. But before returning, there is a call to check canary. Though that function name is not check canary, but the basic idea is to validate whether the canary is actually the original canary or it has been modified. And in case if it has been modified, the program exits, right? Yeah. And there is no return. Pretty self-explanatory, right? So you can understand the basic idea of a canary model. Now the next thing that we have is an NX, or no execute. So if you have heard of DEP, or data execution prevention, if it is more or less the same thing. So what NX does is it marks certain pages as non-executable memory. The pages or the memory areas which are not supposed to be executable are marked not executable. For example, stack is not supposed to be executable. A stack is used to hold local variables and return addresses. And since it is just used to hold some data, it should not be executable. But it was executable by default, so that is why we were exploiting buffer overflows easily. Now, if NX is enabled, then we are not able to execute our payload if it is on the stack without doing something else, right? Another thing is the heap is also non-executable, right? Let's have a look at certain page protections that are by default enforced, right? So let's see what cat does. So what we have done is we have moved to the proc/self, which is the directory of this process, and the maps is a file which lists various memory mappings of various segments, right? So this is the bin cat. You can see there are 3 sections of segments, to be honest, though these are consecutive, but again, so it is the starting address, the ending address. These are the page protections. So you can see that either the pages are writable, which is denoted by W, or those are executable. It is X. So notice any page which has a X written on it, it is not writable. It is readable, executable, and then we have or readable, writable. So this is what the NX is. So if the page is writable, it is not executable by default. What it does is, since stack and heap are writable and you are taking input on in those memory sections or areas, those are not executable by default. Then the next thing is pi. So what pi is, Pi is position independent executable. If you have attended my previous series of about rootkits, we talked about Pi. If not, basic idea for Pi is it generates executables in the form of position independent code, or basically relocatable binaries. So the thing is, there is no absolute addresses in the binary. I think there are a few. No, in case of Pi, there are no. And what happens is, since there are no by default addresses or fixed addresses, even in any section, so you everything is loaded in memory, and then they have a base address, and then offsets are applied to it. So this complicates the exploitation process a little bit, just because we do not know the address of anything while we are trying to execute, right? So the 45 source is something which is more or less found in the big binaries. You do not really see the 45 source in smaller binaries. But what 45 source does is it kind of transforms the basic simple, I would say, vulnerable code into something which is non-vulnerable. So it cannot do that for every single thing. What happens is, if you are doing string copy, right? So what it can do is, instead of just putting strcpy in your code, it will try to see the size of the buffer which is going to take the input, and it will be replacing strcpy with strncpy with the size as the parameter. So it is helpful in a lot of cases, but again, the protection or the strength of a mitigation is decided about how efficiently or how robustly it has been implemented, and not about what it says in theory. I think you're getting my point. Now, Relro is another, as I think probably the last thing that we're going to discuss in the modern mitigation techniques. So what Relro does is, there are a few sections. For example, GOT section, since it is, I think, more or less limited to the GOT section only. So in a binary which is dynamically linked, what we have is dynamic resolution of symbols, which makes possible to generate files which are having library connections, such as if your program is using printf, scanf, or any other thing from any other library. So the functions are resolved at the runtime. But to do that, initially there are, you can say, there are dummy values, because it does not know the address of that function in the library. So what happens is, it resolves at runtime, and since it should not resolve a symbol again and again every single time, because that would be too much of what do you say, not productive, or too much time taking. So what happens is, instead of that, the moment it first finds a function, for example, you are using printf 10 times in the program. So in that way, it will not resolve printf 10 times. Rather, it will resolve the printf first time, and then the next time it searches for the address of printf, the address of printf will be stored in the GOT section. But that is the basic idea. But since it is writable, that has a problem, right? So what Relro does is, Relro comes in, I think, Relro comes in three phases. First one is no Relro. Second one is partial Relro, which is by default if you do not specify any linker options. And the third one is full Relro, which is here, right? You can see the Relro is full. So what the full means, the function resolution is performed beforehand, and all the functions are resolved beforehand, before the actual execution begins, and then the segment is marked non-writable. So what helps is, this helps in protecting against vulnerabilities which write to GOT section and take the execution control. So are we clear, or do you have any questions? Okay, so let's see what's the next thing. So smashing the stack on x86. So this is where the things get practical. So from here we are going to, now the next two topics are more about writing a custom vulnerable program and exploiting it. And the last topic for today would be introduction to shell coding and how to write your own shell codes basically. Okay, so checksec shows the mitigation tech that we, yes, basically. So checksec shows the mitigation techniques that are employed by the binary. In some cases, things are pretty basic. For example, canary bypasses are more or less dependent on the scenario. You cannot bypass every canary checks. Again, same goes for almost every other technique, right? Almost every other exploitation or vulnerability is kind of conditional. It helps basically. So let's suppose we do not see what are the exploit mitigations that which are employed by the binary. So in that case, you might be just going to override the return address and then you debug and then you see, okay, so there is a canary check. So starting with checksec, it helps us to have a little idea about how to approach if we were to exploit the binary. So I think that clears it, right? Okay, moving ahead. Yeah, welcome. So smashing the stack. Let's see, what do we have? CD, XD, LS, CD1 programs. Okay, so there are a few programs. Let's see what 1.c is. Now this is the basic program that we are going to exploit. It basically does nothing inside the main function. It calls the overflow function and it returns 0. In case of overflow, it has a buffer of 500 bytes, but we are using the read function to read 700 bytes from the standard input into buffer. And since the buffer is only 500 bytes in size and we are reading 700 bytes, it will definitely. Okay, didn't get the canary part. Can you repeat? Okay, which part of canary I did not understand, because I was talking about canary in a few parts. So if you can let me know what exactly are you asking, that would be much better. Okay, cool. So see, when we're in checksec, it tells about which binary exploitation mitigation techniques that are employed by the binary. Now, the first one is canary. What canary does is, without canary, the stack looks like this, more or less, right? You have a buffer or the local variables, and then you have a return address. And this is where a function's process stack ends, more or less. Now, when you have a canary here, as you can see, the canary is right there. What happens is the function also inserts, or the compiler also inserts a canary. A canary is usually it is one of the three variants. One is terminator canary, one is random, and one is XOR canary. So I think we all are familiar with what a XOR operation is, right? Now, in case of that, what happens is the function or the compiler actually inserts the canary right before the return address. So before return, we have canary, and the canary is checked when the function returns. So while returning, it makes sense to check whether the canary has been modified or not. Since the buffer is kind of writing from this direction to this direction, the basic idea is if the buffer has overwritten the return address or corrupted the return address, the canary would also have been overwritten. So what happens is, before exit, the canary is checked by a function, which we will see in a minute, right? I mean, we can have a look. Then what happens is if the canary is modified, it is compared with its original value. If it has been modified, the program crashes. And if the canary is not modified, that means return address has also not been modified. And it just lets it continue. So is that clear? Okay, cool. Now let's just compile 1.c minus o, the default settings, right? So and let's see what checkseg returns. So the default settings of the GCC compiler lets you insert a canary. The file has NX by default. It is a Py executable by default, and apparently it has Trello to its full settings by default. So you can understand that to learn or while learning, we need to disable a few of them or almost all of them. Now, how do we see what is the, or how does it work, right? Let's first have a little look at overflow function, right? And this is where, this is the function which is called in case of canary checking. So this function performs the canary checking and it more or less fails or it terminates. So to see that in action, let's just, so it is default 1 and hello. User provided 6 bytes. Great. And what happens if we provided something greater than 500 bytes, or let's provide it 600 bytes, because let's just see what happens, right? And this is your canary checking in action. So it has seen that canary has been overwritten, and since the stack check fail function has detected that canary has been modified, it prints the message stack smashing detected and terminating the program, and it terminates the program. And there's also a code, right? So just to have a little look at the disassembly of the function, we see, so the master canary is at GS, is at 14 hex offset in the value of the GS register. So this is where the master canary is, and it is put off EBP minus C. Now that is the, and initially we have seen that the first thing that it does is reserve the space for local variables and everything, and then it stores the canary on the stack. And this thing is if you can see here, the value is normal return. If it does not match the if the canary does not match, it simply calls this function, which we have seen in action. The stack smashing has been detected. So I think we are clear with the fact what this canary is supposed to do and how it works. Any question? Okay. So start our exploitation part with almost every mitigation disabled, so that we first start learning how to exploit programs, and then we will be adding one mitigation at a time that would help us understand each technique bypass in isolation, right? So let's just, so we already have this binary compiled by default. So if we see this is the basic thing, which, yeah, this is the actual command to disable. So what this does is this disables the stack protector, the cookie part. This makes the stack executable, and this tells the compiler to not generate a pi binary. So this is helpful. Actually, we can bypass the pi based protection and more or less almost every single thing with a memory leak or something. But since we are not deliberately going to put a memory leak in this scenario, we are just disabling every single thing that we do not require, right? Let's just load it again. Sorry. Yep. And let's see what checksec has to offer. So Ralro has been changed to partial. 45, no, 45 was again not in there by default. So pi, the binary is not pi, the NX is not there, and the canary is also not there. To give you a look, let's see. No, FNO stack protector is not for canary bypass. FNO stack protector is to tell the compiler that we do not want canary in our code. So the actual name is stack protector or SSP, right? The mitigation name, but it since checksec has written canary, so I explained it in terms of canary. Okay, let's just disassemble overflow, and here you can see there is no canary, and there is of course no call to check stack fail, which we had here, right? So we had a function stack check fail local, and here if you see there is no call to that function. This is basically something that is right there. And again, if you were to see the differences between the pi based binary and non-pi based binary, have a look at the addresses. So these are the addresses, and in case of a pi binary, which it is, right? So notice that these are not really actual addresses, since this low addresses do not really exist in case of legit binaries. So these are the offsets, and when we remove the pi, what happens is, see, so these are the actual addresses. So what this will do is it will help us in using these addresses directly. So we have that covered, and just to confirm everything, let us see what happens if we send 600 bytes. It should not give us, the program should crash, but it should not give us the error that stack smashing has been detected, right? And yeah, so there is no error of stack smashing has detected, and the core has been dumped, though we do not get a core here just because we need to get the core, and here's the core. So core file is basically a memory dump of when a program crashes. So there was a segmentation fault, and since segmentation fault was there, the program crashed and the program crashed, so the core file was dumped. You can use core file in conjunction with your program. So the basic syntax is GDB with the parameter of the original file or the original program, and then you specify the core file. And you can say the program terminated with segv, which is segmentation fault as it says, and because the address is nowhere to be found. And let's see registers, and we see EBX is again 4141, EBP is 4141, and EIP is also 4141. And let's see if there is some memory or what memory is there. So for that we use vmmap command, which is again a part of Jeff plugin and not a part of actual GDB, right? So these are all sections, basically the binary sections. If you see, more or less, the address is 0804, and then what we have is all the actual executable addresses, since the code has been marked as red. So all the executable things are in red, and either the addresses start with B7 or 0804. So 4141, if we see the EIP, it is nowhere. So this is why we got a segmentation fault. Now, if you print the stack trace, we see we have actually overwritten quite a bit, right? So any questions till this? So let's first have a little bit of idea about how to approach this thing. So the first thing is find the crash. Actually, just make sure the binary crashes, which we have done. Next thing is figure out the exact size of buffer that will allow us to control EIP. Right. So, and the next thing is when the EIP has been controlled, when we have made sure the step 2 has been completed. So the next thing is point EIP to our shellcode. So it is the basic idea that we are going to accomplish right here. Now let's see. So the first thing we are going to do is, since a 600 byte buffer is crashing the binary, what we're going to do is we are going to generate a more or less a unique string or a unique pattern, which will help us identify what were the actual 4 bytes that overwrote the EIP. So when we search those 4 bytes or those 4 characters in the whole pattern, that would help us figure out easily. So true that there's the pattern create, and 600 is more than enough. This is the 600 bytes pattern. Copy it, quit. Let's just remove the core file and just, now it is asking for us the input, and there we go. And this is the state where it says the EIP is this, right? And let's just see where it lands in our buffer. So the command would be pattern search, and there we go. It is 516 likely. So more or less we are at, since we are using a little endian architecture, the Intel microprocessors use little endian for data storage. So we are going to take this one, 516. And just to make sure we have something, we have we have the crash EIP control at after 516. 1 2 3 4, and yes. So here's the core file, and just to validate, let's just load it in GDB again. Actually, yeah. And you see we get this 4242, and here the EIP is 4242, which basically is BBBB, right? And let's see, the BT is, the first thing is there's nothing in at this address, and the next, the return is this C. And let's have a look at what the ESP contains. So thanks to what's in hex from ESP, and the first thing is C, which is the 4 times C. Actually, this after B we have this 4 times C, which confirms that after 516 bytes of input data, what BT syntax does. So BT just prints the backtrace, or more or less the stack trace of what is there next, or more or less where this will return to, and then where this will return to. Basic idea of from where this function will go to once this function finishes execution. So if we see here, right? So in this example, so when we sent this 600 A's, it overwrote the return address. It overwrote the stack so much that we had this many of return addresses in the stack. Now, in this case, since we have figured out that it only requires 516 bytes to override the EIP, we have just sent 4 more bytes from here to there. Yeah, where it is. Yeah, here it is. So this is for EIP override, and these 4 bytes which are next to this. So is that clear? Let's just do this. We have done this. Yeah, the BT command is the GDB. The BT is a GDB command, so it works the same in everywhere if you are using GDB. So I'll let you know which command is the plugin command and which command. So I'll just let you know when I'm using a plugin specific command, so you know which command is in the by default GDB or which command is not in the by default GDB. Right. So we have done these 2 steps. The next thing is to point our EIP to shellcode, which we are going to do this. So I think you know what a shellcode is, right? Or is there somebody who does not know what a shellcode is? Okay, for those who do not know, shellcode is a code which provides your shell in the most basic sense. In a broader aspect, the shellcode is something which gets executed when you control EIP or basically anything, right? So it is more or less your actual payload, which is going to get executed. Yeah.
Hello, sir.
Yes.
I have one doubt. In Linux base right now, after we EIP, we override the ESP1, right? With C.
Wait, what?
First of all, we override the EIP1, okay? Then we go for ESP.
Okay.
So let's say right now you're using means sending EIP BBB, and then for ESP you are sending a C, right? But when I'm doing in Windows, before sending ESP, there's 4 more bytes, which I
Okay.
don't know what's that.
Okay, see, those things are more or less the software dependent thing. So it is not the case that just after overwriting EIP, the next 4 bytes on the stack will be what you have sent.
Yeah,
So
that's the thing, right?
it depends on the software. What you have to do
Okay.
is, and this is one of those things which I think I need to clear. The exploit development scenario is more or less you have to work with what you are given and not how things should be. Right. It makes sense that if you are sending this data, which is one continuous chunk of data, and let's suppose what your question was, right? That before this, you also have 4 more bytes, which you don't know where they come from, right?
Yeah.
So it is really not worth anything. You are trying to figure out why that 4 bytes are coming from and why they are there, when if you are sending one input which is continuous and does not contain any characters which should be breaking your input, should not be there, right? But the thing is, the program is processing the input that way, and all you have to do is just make with that thing.
Okay, get it. Thank you.
Yeah, okay, great. So is that similar to jump ESP? What is similar to jump ESP? Okay, till the time you write the sorry question properly. Let's see what we're going. Now, the 4th byte he used before in Windows. No, what he is saying is, since our inputs 4 bytes directly after overwriting EIP is this, his input or his program actually has some random 4 bytes before these 4 bytes show up. So jump ESP is something that we use to jump to ESP. Okay, cool. So let's just have a look at what we are going to do this. So now only the task is, since we have controlled EIP and EIP points to the code which needs to get executed, the task is simple, just point our EIP to the shellcode. But what happens is you need to figure out how you are going to do this. So there are 2 things where, or there are actually 2 places where you can place your shellcode. So let's have a look at the structure which we have right here, right? So 516 bytes, then EIP, and then space. So we have some space after overwriting the EIP as well. Now there are 2 places. First thing is you can put your shellcode here, or you can put your shellcode here. In any case, you have to make sure to provide the address of shellcode to EIP. So that is more or less what the basic strategy would be. Now, since we have to, provide the address of the shellcode, it does not really matter whether we are putting it after EIP or before EIP, until unless there are some space issues, right? So now, in case you are trying to put your shellcode after EIP, you need to figure out how many bytes you have before you run out of space. But we are sure that it takes 516 bytes, or we have exactly 516 bytes before the EIP overwrite happens. And this is what happens is, since we already have 516 bytes, and which is more or less a very good size in case you are even trying to put the shellcode from Metasploit as well for the Linux, anything, right? You might want to execute something, you might want to have a reverse shell, you might want to have a metapeta shell. I believe almost every single Linux payload which should be or can be used is more or less 516 bytes or less, unless you are trying to really just fill the space with your shellcode. So I am going to take the first part, or the first path. You can try and have the second path as well. So both paths are the same. There is literally no difference. So for this, we need to see where we need to first figure out what is the location of the buffer, right? And for that, we are going to use GDB. Let's just remove the core file. And let's just run this file. So we are at the first breakpoint. These are the registers and the current scenario. These are the E flags, the segment registers. This is the stack, right? This is the stack, top of the stack points to this. And this is how it works. Like, since we have, let's just disassemble main, right? And the in main we call overflow function, which is right here. The instruction is call overflow. The next instruction after call overflow is this move ex0 with the address. This, since 0804 is more or less common with everything, let's just say 84CD. And when we are at this breakpoint, so what happens is when you call a function, first thing happens is the address of the next instruction, which is this, is pushed on the stack, top of the stack. And since we are at this function, and the top of the stack is this address, which the Jeff plugin has already done the dereferencing part for us, and we see that it is a pointer to move ex 0, which is the same if you see here, move ex 0. And this is how it works, basic idea. So this is on the stack, and if we disassemble overflow function, we see the read function is getting called with an argument. So this is the buffer address. This is 0 that we see, which let's just shell. Yeah, so this is the basic idea, right? So we are calling read with 3 parameters, 0, buffer, and 700. So the first parameter is 0. Second parameter is this ebx ebp minus 200. So anything which is usually ebp minus is a local parameter, and anything which is ebp plus is a anything which is ebp minus is a local variable, and anything which is ebp plus in usual cases is a parameter to the function. Since our function does not have any parameter, let's just move there, right? And we are pushing 0x to bc as the length. Now we have to figure out where this ebp minus 200 is, because ebp is more or less dynamic in our case, right? So let's just put a breakpoint at this location. Overflow plus, we are going to put a breakpoint, first breakpoint at 36, and the next breakpoint at 43. So which will help us see whether the data we introduced is right there or it is not stored there, right? And then the next thing we are going to do is put a breakpoint at this, at 6. Sorry. So we have 3 breakpoints. First one is to resolve the address of the input buffer. Next thing is to confirm or to see whether the data actually starts there or not. And the last thing is at the return. So let's just continue this. And the top of the stack contains this, which was executed or which was pushed on the stack by push ex, and ex is e minus 200. And since ex has not yet changed, we see this, right? Ex is still the same thing. Now, since we are sure for now we are going to put a string there, let's just disassemble it as a string. At this address, more or less unknown particular address, let's just have 20 words in hex at this address, and these are the 20 words in hex. Now let's continue. Now it is asking for input. Let's set a few A's, and again let's have a look at this same address, and we see there are A's, right? So here we go. Instead, let's just do an XS or print it as a string. A repeated 61 times. And then there's a new line. Since the read function does not, you can say it does not filter out the new line, it puts the new line there. And you see after 61 A's, we have a new line here, which is represented by 0A. So the read does not provide a null terminator, and it does not replace a new line with a null. So there's that. We have to make sure it works that way. Okay, so we have to make sure the address is this one. So what we have to do is we have to put this address as our EIP. So let's just see which is address is this. Now we have 516 bytes total, right? This is our space, but our shellcode is, let's say our shellcode is not 516 bytes. Let's say shellcode is 50 bytes, or basically any number which is less than 516, because we cannot put anything which is greater than 516 and 516 bytes of space without compromising with the return address. So what we can do is we are going to put some junk address or something else. So our buffer looks like this. The buffer would look like something, let's just say we are having C, multiple C's as 516 minus 50 times, and then we are going to put a shellcode, and then we are pointing to EIP, which is the same address, and then we will just be done with this, because what this will do is the EIP will contain this address, and when the function returns, it will jump back to this starting buffer, and then from there it will execute the shellcode, right? Another thing that you can do is, or what people usually do is, put a nop here. A nop is represented by 0x90, so that is, you can also do it this way, right? So I think that is clear, right? Let's first have a look at what our exploit1.python script does. So what we are using here is the shell code is this, which is I think 40 bytes or something. Let's just have a look at the size of the shell code. So yeah, so the shell code is 30 bytes in length, and let's just open it. Wait, so there is not, I cannot do a gedit. Yeah, so this is basically a framework for or basic organization. Now this is the return address, and as you can see, the return address is different since it was different last time. So we need to fix this return address, and we are packing it as a little endian 4-byte word, which is done by pack function. You can obtain the pack function from the struct header or the struct library. And what we are doing is we are doing nops, then shellcode, and then some again nops, and then return address. So the first thing that we have to do is disable ASLR. Or else the stack address would be changing every single time, and we would end up actually brute forcing the stack address, which is not really a good idea, but again, things keep changing, so let's just remove that for now. Right. And let's see what happens when we do this. Unfortunately, we have to again figure out the stack address. Overflow plus, it was last time 43, no, it was 36. Okay, so the return address is the buffer address is this, so it is the same this time, right? Yeah, since we have turned off the ASLR, of course it would not change. Yep. Let's just quit this thing. Yeah, when ops is given, is there any way to determine how many of them is to be provided, or we just randomly provide some nops? Why would you provide randomly nops when you already know you cannot, you only have space for 516 bytes, or and you also need to include your shell code in that space as well? So why do you think anyone would go about providing random number of nops? Okay, so let's just edit it in our Python file, right? And yeah, great. So this is something, and let's just have it here. Yeah. So control O. Okay, looks like my concept for it is not clear. Then how do? Okay, so let's have a look again at the calculation of knobs. Okay, so we have 516 bytes, and in this you have to put knobs and shellcode. So it makes sense that you subtract the size of shellcode from original size, which is 516 here, and then the value you get is the number of knobs that you can place. So because number of knobs plus shellcode is 516. So I think that should be it, right? Okay, great. So moving on, the basic idea is this is where we are moving, right? So let's just have a look again. So what we have is, this is bufflen is 516. We have already declared it. Length of shellcode. What this does is it actually helps us to keep the script dynamic, just because let's suppose you change the shellcode from a 30 byte shellcode to a 200 byte shellcode. So the next time you don't have to modify this line, just change the shellcode and you're done. Now the next thing is we are preparing the knobs, which is okay, we already discussed it. And after this we have the return address, which is 358, basically starting of a buffer, and knobs plus shellcode plus return address. And we are doing it a print because it is taking this as an input from the standard input, so we need to redirect the input, right? So let's just do this, exploit, and let's just do temp1, right? And when we let's just verify it in GDB. Overflow, run it with the temp1, and we are at our breakpoint. So what happens here is, let's have a look, right? And since we know that the address is what we have put here, the address would be 358 F358. Let's just put a breakpoint at return, which would help us see where the execution is going, right? Just continue, and you see that the execution is actually going to this F358, which we have put here, right? The EIP358, which we have obtained from previous executions in GDB. And if I do an SI, which is basically the single step, it goes to knob and it is executing our knobs, right? So this should be it, right? More or less. So yep, we have also done this part. So did we get the shell? Let's see, right? And since it is already in temp1, let's just okay, unfortunately we get a illegal hardware instruction error. Now for that, what we can do, two things. One thing is, since addresses are somewhat different inside of GDB and outside of GDB, the stack addresses, because the environment changes. So what we can do is we can try to modify this address. And another thing that we can do is to rearrange our structure of the buffer, right? So let's just rearrange it. Let's do it this way, plus 90 into 100. And let's do it this way. And then we have a segmentation fault, unfortunately. So we need to now change the address a few bytes here and there. So instead of 348, let's give it, instead of 358, let's give it 388. And again, we have a segmentation fault. Let's just run the core, and we have the core. And this is where things get problematic. You need to, there was a problem in 388. Let's see what is there. And unfortunately, we have some bad values, right? So what we need to do is we need to debug our shellcode properly. And for that, we again turn to GDB and break overflow. Disassemble overflow, break at overflow plus 86. And we run it with temp1. Continue it. There 388 is nops again, right? So let's just have a look at what do we have here. Examine, let's say 200 bytes in hex, which would be 800 bytes. Actually, not the byte. The bytes are 200. This is 800 bytes. And things are a bit different here. This is the return address, I believe. Yes. So this is the return address. And before going to, this is the starting part of our shell code. Yep. This is where the shell code starts executing. Actually here, EB0C. Right now we have to see whether our shell code is properly inside there or not. First one, EB0C5B31C9. Okay, so what we see is our shellcode is as it is, so there should be no problem. Right, so let's just stepping it one at a time. Yeah, so this is our shellcode basically. this is where the shellcode starts. So XOR ECX, yes, multiply ECX. Yeah. So here we see that the program is getting executed. Process is executing shellcode properly. So what happens is we just need to arrange the addresses. 388 we can have. So instead of doing that thing, what we can do is let's just and unfortunately the address is wrong, so we need to just keep fixing it until unless it goes to somewhere we require it. Let's just do it again. And this is a little problem with this thing. Let's try it some other way, right? Get bundle.txt with get, and all we need is to fix the address actually. So and there we get our shell, right? So this is what this was all about. So is that clear? And yeah, we got the shell, right? Okay, so any questions? Okay, clear, cool. So this is the basic idea of Stack Overflow. Now, in theory, as we move back to our awful illustration, we have this binary crashes, yes, figuring out the exact size of EIP buffer, which helps us control EIP, easy. Point the EIP back to a shellcode, which is also easy. I mean, you're just pointing it back, so you just need to fill in the address where to jump to. And this is the hard part. So what happens is, in case of GDB or when you're debugging something, the execution environment changes a little bit. So the offsets are different. And if we move back to GDB here, what we did here is we saw that the program or the shellcode executed properly without any problem. But here we see, I mean, outside of GDB, it was not working clearly, right? Let's just see, it works fine. Okay, cool, it works fine. And let's just exit it. And let's just have a look whether we can do it this way as well. I don't really think we should be having any problem. And yeah, it works fine. So either approach is fine. You can write to a file and then cat it, or you can just execute your script and just pass the input to it. So now moving on to the last subject, last topic which we had for today is introduction to shell coding. So we already talked about what a shell code is. We have seen it in action, how a shell code is executed and everything. Now, introduction to shell coding, which I will keep it very brief because we have already passed the time which we were allowed to, right? Okay, great. So before to write our shell codes, we usually use assembly language just because you can write the same thing in C or any other thing. But the thing is, it introduces a lot of code which you would not want it. For example, let's see how much code is generated when we are trying to execute something. So hash include instead.h because that is the file for system calls. Let's do an execv which we used previously. Let's just point it to bin sh null and null, and just this thing gcc 1.c minus 01. Again, no, null is not required. You can actually, and here is our shell, right? So that is what we expect from an execv bin bash or bin sh call. So let's just do an object dump. Okay, let's just do 24. So this is the disassembly of our main function. And you see, just to call an execv syscall, what we are doing is, so this is the second null, this is the first null, and then this is the LEA, and then this is pushing it. Then we are moving EX into UVX because things will change. And then it is calling the execv PLT, which will then get resolved during runtime, and then again it will move to the glibc wrapper of execv. From there it will call the execv syscall. Right? If you don't know what execv is, so execv is a syscall which executes a program. So if you want to execute some program, just call execv with the parameters. So this is the file name, this is the argv or runtime parameters for that thing, and this is the environment pointer. Now these both can be null, so there is no problem, as we already saw. And the file name, in our case, it has been /sh, right? The shell which we want to execute. Now, in case of writing the shell code, we just cannot have all this, because to call the glibc wrapper, you need to also link your glibc to it, which the shell code is a problematic part. But again, I mean, yeah, the program would be using glibc, so should not be a problem. Now this is quite ugly, and it really depends on how these instructions are generated by compiler to compiler version. You just cannot put these instructions copy paste into your assembly file or any other thing and just let it work, because at the end of the day, when we are using a shell code, as we saw, right, this is the shell code that we are using, right? So we are using the shell code as the executable bytes, or actually the bytes which will get executed. So instead of injecting this part, the assembly part, we are injecting this, the actual machine code that we are getting from these instructions. And since this is a relative thing, ex minus 0x19, we just cannot do this. We cannot take this, and then again there's the null byte here, which in most cases it will terminate our input. So we just cannot copy paste this thing. So what we do is, instead of that, we write our own custom shell code in assembly language and use this. So the basic idea of a shell code is, let's have a look at shell code. Sorry, shell coding basics. Coded in assembly. And since we are using assembly, we can call syscalls directly without glibc interference, right? So to call syscalls, basic funda is load the registers properly, which if you do not know, there is actually there are multiple calling conventions. So we call this calling conventions. A calling convention defines which register will contain which value and how how those values are going to be used. So since we are on x86 Linux, we are using the x86. Well, this is actually Linux ABI calling convention, which we are using. So the Linux ABI calling convention states the syscall number is going to be in EX. First parameter is in EBX. Second parameter is in ECX. Third parameter in EDX. And the remaining ones, I'm not really sure about fourth and fifth because probably I forgot about that. So remaining parameters are pushed on the stack, if I'm not wrong, pushed on the stack in reverse order. Or I think you can also push fourth and fifth parameter as well using the ESI and ADI registers. But since our program only requests, since our shell code or our syscall only requests 3 parameters, we are concerned only with these first 4 registers, right? Now, the basic idea is first figure out the syscall number, right? The basic idea. This is what we need to be doing. Now, to find out the syscall number, there's a file in Linux which is by the name unisted.h. The unisted32.h is the one which we usually look at because it contains 32-bit syscall numbers, right? So this is the file which contains the syscall numbers. So if you see, this is the unisted header for the 32-bit, not the .h which gets included, but this is the file which contains syscall numbers. So exit is 1, fork is 2, read is 3, write is 4, and execve is 11, right? So the basic idea is, okay, for execve we have figured out it is 11. Load registers. So EX equals to 11. Sorry, 3 is actually 2.1. EBX should point to bin sh since we want shell. And as we saw, ECX and EDX can be null, right? So if we see it here, right, get 1.c, the second and third parameter can be actually null. So there is really no point in setting those things again. This is where ECX and EDX come to null. And while we are going to write our shellcode in assembly, it goes without, it goes with common sense that you need to know assembly. And the basic idea that we are going to use is, to move something, that is move EX11, move ECX 0, move EDX. You can move ECX into it, or you can just move 0. It will be the same thing, right? And move EBX. So in assembly, you cannot do this thing, right? Bin bash, because it will just take 4 bytes. Probably. I don't really think that this works this way, but again, yeah, okay, this will just take first 4 bytes and put it into EBX. But we need a pointer to this thing and not this as a string. So for this, I have already written the shellcode which I have used. So that was my own shellcode. And let's just have a look at exec.sh. ASM, and let's just copy paste this thing so we can have a look at this in a proper manner. So this is where the shellcode comes in. Now we are telling that the section is text section just to make sure that this is the executable area. The start is the global symbol because you need to export start as the entry point of the program. Now we're doing a callback. So we are actually doing a jump to a label which is referred to as callback. And from there we are calling another label which is exec. So what this does is, as we discussed, that when you make a call, or you can, when you execute the call instruction, it pushes the address of the next instruction on the stack. And since this is the next, there is no instruction but it is a string, its address gets pushed on the stack, which we can pop into EBX, which we require here, right? Pointer to the shell. Now EBX contains a pointer. Okay, we have made sure that thing. Now to remove nulls from our shellcode, what we have done is we are XORing or XORing each register with register, which effectively makes a register 0. So when you XOR or XOR a value with itself, you get a 0. So we are putting 0 into ECX, then we are multiplying ECX. So what the multiply instruction does is it will multiply ECX with, it will just actually do this thing, ECX with EX, and the result would get into EDX and EX, sorry, EX. And since it is a 0, so the result is 0, 0. So with one assembly instruction, we are setting 2 registers to 0. So that is one way of reducing instructions, right? You also need your shellcode to be as compact as it can be. Now, the next thing is we cannot put a null after bin sh, but since it is a string, the OS requires us to have a null terminated string, right? So what we do is we move a null after bin sh, basically. So we are patching it at runtime. So while generating this, make sure that at the time of generation there are no null bytes. We are just moving 11 to AL, which is the lower or the lowest byte of EX register, and we are calling the interrupt 0xAT, which makes the syscall. So all in all, it is actually a very simple thing. I mean, the idea is very simple if you look at this thing. So the first thing is figure out the syscall number, then figure out registers, which you can, figure out the parameters which you can see from the main page. Just load the registers in a proper way and execute the syscall. Simple as that. And here we go. We get a shell. So any questions? Line 43 to 45 again. So line 43 is 43 to 45. Okay, there are only 2 lines. First thing is multiply ECX. So at this point, ECX is 0. So when how the multiply instruction works is, so this is the way multiply instruction works. Let me just make some space for this thing, right? So this is how the multiply instruction works. So it by default, it takes, actually multiply instruction takes only one value and it multiplies this one value with EAX. So the multiply ECX will expand to this thing. And since ECX contains 0, so anything multiplied 0 is a 0. But since we are multiplying a 32-bit value with a 32-bit value, so the result will be stored in EDX and EX, where upper 32 bits are EDX and the lower 32 bits are in EX. since the result is 0, so it will set edx and ex both to 0 at the same time. So we are doing this with a single instruction. So you can also, instead of doing this, you can just move ECX into EDX, which will again set EDX to 0. And then you also need to, or you can do move 0 or move ECX, which will also do. Sorry. So here it requires us 2 instructions, but we did the same thing in a single instruction. So this is why we use this thing. Now moving on to like what, 43, sorry, you asked for 43 to, yeah, okay. So the next thing was this thing. So move EBX plus 7 ECX. So the thing is, this is not a valid path, right? You cannot execute this thing. First thing, this is not a null terminated string. So, and second thing, sorry. Yeah, so let's just see this thing. So you just cannot execute this thing because there is no such file or directory. And again, when we see this, this string is a null terminated string. You need to pass the address as a null terminated string. But we cannot have nulls in a shellcode because that would make it restricted to only a few input calls. Now, in case there was scanf, so it would, just not copy anything after this thing because there's a null. And since if we see our shellcode, if we see our exploitation mechanism, we have this thing. So the shellcode contains a null because we are just not using AAA here. It will not copy the rest of the things and we would not be able to control the return address. So for that, what we are going to do is we are going to use this as a string, and then these 4 bytes, we will make them null by moving the value 0 at that location. And since ECX is null, it sets these things as null. So after this, what happens is then SH gets transformed into bin. And now our first parameter is a null terminated string. So is that clear? Okay, so I hope that is clear. So that was a really quick primer on shell coding. We can have another extended session. Okay, yeah, maybe a silly question. Why given bin sh at the not bin sh? Okay, we can give bin sh as well, but at the end of the day, we need to place nulls after the string. So these are the nulls, and we need to null terminated. Now let's consider this line, right? So this is the line. Now let's suppose we are not using this thing and just we are doing this thing, right? What can happen is, since we are not doing this way, we need a null here, and we cannot place a null here because it will terminate our input. So we specifically need this thing. Let's suppose we have this thing and the shell code is just, I mean, yeah, you can do that thing because the return address would be there and then it will just null it. The basic idea is you can do anything as long as it does not compromise with anything or any other thing that you are trying to achieve. Maybe let's suppose it is not execv, but some other function which also requires a bin sh, or maybe another string which needs to be a null terminated. But your shell code is, let's suppose there are other instructions here as well. Now, if you are not providing 4 A's here, right, which are being modified by this to a null, it will modify the next 4 bytes. So it really depends on the scenario to scenario. You can just have anything as long as things works, as long as you are able to, get your shell code, execute a shell with this and something here, it is fine. So there is really no restriction that says you need to make it this way and then make it null. You can have anything as long as it works. The idea is at the end of the day, you need to get the shell. How you get the shell, that is a different thing. There is no restriction, right? Okay, great. So any other question? I think we can conclude the session. So this was the basic introduction to exploit development. In the next session, I am planning to, let's just remove this kind of ASLR bypass. Though ASLR bypass is not really something that I would want to cover in the next session. In the next session, I am interested in covering NX bypass, which is basically, getting your shell executed when a stack is not executable. And we are also planning to cover return to libc to get your shell. This is what we are, this is what I am planning in the next session. We might as well cover ASLR bypass. Not really sure. We might be able to do that depending on the time what we have at hands, right? And thank you very much for your support and I would say participation.
Hi, Himanshu. Okay, so it's done.
Yeah, okay. It's done from my side.
Okay, so let's have a look. Thank you guys for joining us today. And what are the things? Ashok Mishra, Ashok Krishna. Thank you. Thanks a lot. Learning new things. Yep. You will be getting the sessions on YouTube. Just search for InfoSec Trainer. You'll find the profile. Okay. Thanks, animation. Are Doshi sir, abhi ho. Okay, so we have few more sessions upcoming. One of them is Fun with Malware Season 5. And that will be about fileless malware from Demigod. He'll be taking care of that thing. So hope I'll see you guys tomorrow as well. So have a good time. Stay safe. Yes, guys, it will be very good. Like if you can fill up the feedback form, so that will help us to improve the content and stuff like that. So yep, thank you, Himanshu, for taking care of today's session.
Yeah, welcome.
And Mishraji, I'll see you tomorrow. And hopefully I'll see you guys tomorrow as well. So take care and end session here today. Okay then. Bye.
Bye.
Yes.